Welcome to Mr. Hamilton's Math Bites. This video is an introduction to Pascal's triangle, where we'll look at some of the patterns. Our next video is going to look at how Pascal's triangle applies to binomial expansion. So the first thing I want to look at is Plinko. Some of you have seen The Price is Right. In fact, hopefully all of you have seen it by this time, and one day hope to win a whole bunch of money or prizes on the show. I actually know someone who went down to go on the show, and he had tickets and everything. He got there about an hour before the show and found out that his tickets weren't valid, that he had to show up like 4 hours before the show should he actually have wanted to get in. So just some information if you ever want to go. Anyway, let's focus on the Plinko game. This is one of the favorites because I think you can win up to $50,000. You can see there that there's a $10,000 prize in the middle, and if it falls in there, you win 10,000 bucks. And if you guess properly to get the 5 Plinko chips, you can drop all 5 in, and they all 5 can win $10,000. So I think that's only been done once in the history of Plinko, but it's still a very interesting possibility that could happen for some people. So my question for you is, what's your winning strategy at Plinko and why? For example, where do you drop that little disc that it's going to bounce down and into the Plinko board? This might help simplify things for us, because the Plinko board really is a bunch of pegs, and this is a very simplified Plinko board. If you drop a disc in, it's going to hit a little peg right there and bounce either to the left or the right of the peg, and then it's going to fall down to the next peg and bounce either to the left or right of that peg. So it's really about finding the number of paths that the Plinko chip will go down the board. There are a few lessons for today. The first thing is we want to decide where to drop the Plinko chip. And if you win $50,000, just remember that I gave you this. I helped you find the strategy when you go and play Plinko. The second goal today is we want to investigate patterns in Pascal's triangle. And the third goal, which we'll do in the next video, is we want to use one of these patterns to expand binomials effectively. This video is supposed to be about Pascal's triangle. So let's simply look at a triangle of these pegs and see how this works out. If you were to drop your little disc, let's say your disc looks like that, in through these 2 pegs at the top, you would have one way to get through those 2 pegs. And then that disc would either bounce this way or bounce this way off of this peg right here. And so there would be one way to get here and one way to get here. Then the disc would bounce off this peg if it went to the left, and so it would bounce either this way or this way. So in other words, you would have one way to get here because it would have to constantly go left, or to get to this middle place, it could also go down to the right here and then bounce across the left. So you actually have 2 ways to get here. And then the only way to get to this point right here is by going right constantly. So you have one way to get there. If we continue that pattern, if we were to bounce off of this peg and go this way, there's still only one way to get there, constantly go left. But if you were to bounce all the way down to this spot right here, you could bounce off of this peg or this peg to get there. And remembering that there's one way to get there and come here. There's 2 ways to get there and come here. So really there are 3 ways to get to this point right here. Likewise, if there are 2 ways to get here and you come to the right, and 1 way to get there and you come to the left, there are going to be 3 ways to get there. And then there's only 1 way to get to this point over here because you're bouncing constantly to the right. Now if you continue that pattern, I hope you're seeing that what happens is you just add the 2 numbers that are on the diagonals above and you get the value that's below. And that is the basis of Pascal's triangle. Pascal's triangle are those numbers. We could write it out as saying it's a triangle made of numbers such that the 2 diagonals above add to the number below. And so if you're thinking about a Plinko strategy here, what you're thinking of is if I drop this disc up here, in here, I want to drop it in as close to the middle as possible. If you drop the disc in, if we continue and put pegs over here, and over here, and over here, and over here, think about it and realize that there are actually going to be fewer ways to get to the middle than if I drop the disk in the middle. So Plinko strategy, disk smack in the middle. Maybe the most boring strategy, but it's the best odds. So just to show without all the dots on this, I'm just going to redraw this Pascal's triangle below and we'll continue the video. So here's Pascal's triangle without all the dots, and I hope that looks a little more organized and not as cluttered for you. There's one important detail we need to know about this, and we number the rows a little non-intuitively. The first row is numbered 0. The second row is numbered 1. The third row is numbered 2, etc. Just remember that we always start at 0. And so there I've drawn the first 7 rows. Now, at some point, you may be asked to expand this out to 12 or maybe even a little bit more. So what I would do is I would continue that pattern out and have a page in your notes with just Pascal's triangle on it and expand that out to at least 12 different rows. Now there's some very interesting patterns that we can recognize here from Pascal's triangle. And the first pattern I want to point out is quite a simple pattern, but nonetheless it's something that we should be able to come up with a recursive formula for. It's the counting numbers, 1, 2, 3, 4, 5, 6, etc. And there it is, if I could circle it properly on the other diagonal. Now, that sequence is an arithmetic sequence. Why is it an arithmetic sequence? Well, the a value is equal to 1, and the d value is also equal to 1. We're going up by 1 every time. So what that means is if we're talking about a recursive formula, what we should be able to do is we should recognize, well, the recursive formula is Tn is the previous term plus the d value. So it's plus 1, where T1 is equal to a. The restriction has to be there that n is greater than 1, and also that n is the natural counting numbers. The general term for that we know is Tn equals a plus n minus 1 times d. Or more simply, we can just say, well, it's just the counting numbers. So it's just n. Because if it's the first term, it's 1. If it's a second term, it's 2. If it's a third term, it's 3, etc. So it's fairly straightforward to do. And the only restriction there is that n has to be, we could say it's greater than or equal to 1, or we could just say it's the counting natural numbers. Because natural numbers are 1, 2, 3, 4, etc. So that's the first pattern. That's not that interesting to see. So let's just recognize a second pattern here, and we'll continue on. The second pattern we can recognize, and it may not be intuitively obvious at first, is this pattern right here, and it's the exact same on this other diagonal. I encourage you for a moment to stop the video, pause the video, and see if you can figure out what the pattern is. We've seen this before, and if you haven't seen this before, you'll recognize this very shortly. So what we're going to do is we're going to just draw a picture to see about this second pattern. 1. There's 1. 3. There's 3. 6. There's 6. 10. Are you seeing it yet? I hope you are. These are known as triangular numbers. Almost there for 15. Takes a little while to draw 15 circles here. But they're the triangular numbers. And so they're triangular numbers because if you pile up coins or anything like that, you see that it makes a shape of a triangle. So let's see if we can determine the general term and the recursive formula for triangular numbers. The first thing we want to do in order to recognize that is just put things together organized in a chart form. So what I'm going to do is I'm going to first list the row number or the term number, and then the term value, and then I'm going to write it in terms of the previous term. In terms of Tn minus 1, that's the previous term. Let's start by writing the first one. The first one has a value of 1. In terms of the previous term, well, it's the first term, so it doesn't have any previous term. The second term has a value of 3. In terms of the previous term, it's that previous term, and we've added 2 to it. The third term has a value of 6. It's the previous term of 3, and we've added 3 to it. The fourth term is 10. It's the previous term of 6, and this time we've added 4. So you can see that we're counting up, we're adding one more every time. And so if I go to the next couple of terms here, you can see it's 10 plus 5. And again, we're adding one more extra. And then the sixth term being 21 is 15 plus 6. Again, adding one more extra every time. But how do we put this in terms of n? If we write this in terms of n, the first term, being 1, is simply n. So what that means is it's 1 times n. The second term, which is 3, is, if we look at this, it's 3 halves n, or it's 1.5 times the n value, right? Because we had 1, we've multiplied it, or we have 2, multiply 2 by 3, which gives us 6, divide by 2 gives us 3. So what we have here is 1.5 times the n value. And we could write that out, probably not intuitive, just follow my pattern here, as 2 plus 1 divided by 2 times n. That third term we could write out as 4 divided by 2 times n. If you think about that, 4 divided by 2 is 2. The n value is 3. So 2 times 3 is 6. And that is what that third term ends up being. We can write that out as 3 plus 1 divided by 2 times n. That corresponds to that one, that corresponds to that one, and that corresponds to that one. Let's go one more here and see if this pattern continues. The next one I can write out as 5 over 2 times n. So for that fourth term, which is 10, 5 over 2 is 2.5. 2.5 times 4 is 10, because the n value is 4. So we could write that as 4 plus 1 over 2 times n. And we continue that every time for all the values. And so from this, we can write out and figure out the recursive formula. This is going to give us the recursive formula. And over here, this is going to give us the general term. It's really not intuitive. I'm sure you're like, well, where did this come from? It's very difficult to come up with this. But some of you may be very logical in this way, and you were able to figure this out on your own. If you weren't, that's okay. The key now is to recognize these and see where this comes from. The recursive formula could be written as Tn is equal to the previous term plus, well, we're adding 2 when n is 2. We're adding 3 when n is 3. We're adding 4 when n is 4. So we're adding n to that. So the recursive formula is actually very straightforward. The first term is 1. And the restriction here is that n has to be greater than 1. And technically as well, we could say that n is the set of all natural counting numbers. And that's a recursive formula. That's all there is to that. The general term, which was a lot more difficult to figure out, we now can arrive at as well. And that can be written as Tn is equal to, notice that the 2 here corresponds with the n value of 2. The 3 here corresponds with the n value of 3. And the 4 in the next one corresponds with the n value of 4. So what we can do is we can write that as n plus 1 divided by 2 times n. And here the restriction is that n has to be greater than or equal to 1, so we could just say that n is the set of all natural counting numbers. And so that's the general term in the recursive formula for triangular numbers.